I'm going to talk to you basically to boil this project down into a nutshell of how we're going to take the detector that you're all carrying around in your pocket and turn it into the next powerful tool in the fight against counterfeit goods. So if you're not familiar with the problem, we'll give you some numbers here for a little bit of a reality check. If anybody flew here today, roughly 2% of the parts on the plane you took are fake. That's exciting. About 75 billion in counterfeit medicines are sold every year and $100 billion in counterfeit electronics. Globally, it's almost a $2 trillion problem. So there's a huge potential value capture if you can take some of these counterfeit goods off of the market. So let's look at a couple of headlines. It's not just money either. You've got baby milk blamed for 50 deaths, counterfeit cancer drugs, counterfeit parts in military aircraft, people dying from fake vodka. Although if you don't drink Czech vodka, I guess you're okay. And also, counterfeit electronics in, the goods that we use all the time, your smartphones and computers. And you might think, well, maybe this is something that happened a while ago, but we're on top of this, right? Not so much. These headlines are from really the last year to the last 10 years. So the state of the art today in anti-counterfeiting technology are ubiquitous features that you can see with your eye pretty easily on a product that are fairly easy to read, like a barcode or a QR code, but also fairly easy to fake. I can print one out on my printer. But there's a whole suite of other technologies out there that are very, very small tags that you can't see very well, covert tags. But they require bulky and expensive readers that are usually only used by a couple of, let's say a small skilled workforce. Other things that are out there as well, they are either very expensive or they require a lot of real estate on your packaging. So there's an impetus not to use those. So our approach is, well, why don't we just use the detector in our pocket? What if we had a way to make a very small but very secure and inexpensive and also visually appealing way to authenticate goods? So a little bit about what I mean by this. When I say secure, I'm talking something that a central bank would use. We've had interest from companies that print currency, and we may yet go down that route. When I say small, I'm talking on the order of 100 microns. So the total packaging real estate would be about a square millimeter. When I say inexpensive, I'm talking about less than 1/100th of a cent per unit, which is 1% or less of the cost of an RFID chip, to give you a benchmark there. So the way that we do this is through smartphone readable microbarcodes. If you look up here, this is an actual picture taken with an iPhone plus a small amount of magnification, and the sequence of colors on each individual particle can carry information about the product that you're trying to read out. And you can also imagine if you take a suite of, let's say, 10 or 12 particles on a product, that just expands the size of your code and the amount of information that you can carry. And to give you an idea of the number and the numbers behind it and what our encoding capacity really looks like, with 10 particles, 6 colors, and 6 stripes per particle, we can barcode not only every manufactured product ever made, but every grain of sand on the earth. So that's pretty good. Not bad. All right, so how do we do it? The first step is to take really tough ultraviolet curable polymers and mix them with exotic nanocrystals that will emit different colors when you shine a near-infrared light onto them. Then we take that fluid and we put it into a microfluidic device that combines photolithography with very, very narrow fluidic channels to make small stripe-encoded particles. So what you're seeing here is basically UV light polymerizing across the streams to make a striped particle. One thing that you'll note is that the photomask that we show there, which defines the shape of the particle, that's interchangeable. So you could, instead of just rectangles like I showed you before, you could also make company logos, Nike swooshes. You're really limited by your imagination for the most part. And then you place the particles down onto a product and snap a picture with your phone to decode it. And the way we're envisioning it is you take a picture with your smartphone. It would go, either be decoded on your phone for some applications or sent off to the magical cloud, which sends you a verification answer back. Either a check for authentic or a red X for non-authentic. So it's now time for a bit of honesty. Maybe it's the first time you've been honest with yourself all day. You're all thinking it. Why can't I copy steal or spoof this? So the first reason is physical security. The manufacturing process is very, very challenging. It's been in works at MIT for about 10 years. Now, for those of you with a team of North Korean scientists and suitcases full of cash, you might say, well, fine, I can copy your manufacturing process, no problem. Well, it turns out that we're able to actually layer security into these particles by design. So not only can you have colored stripes, we can also add other tagans that are either difficult, if not impossible, for you to detect and copy yourself. The second is if you're actually putting a unique barcode in each product, stealing those is very unprofitable. What you want to steal is something like a hologram, where if you have a bunch of holograms that are all the same, you can put them down on a bunch of identical particles and make your quick buck. But stealing unique barcodes just isn't really going to cut it for you. And as far as spoofing, in other words, basically making a fake signal that the phone would detect, we're on par with other technology as well, neither at an advantage or a disadvantage. So a couple of the quick features about this. The polymers that we use to make the particles are modular and they're industrially tough. So they're heat resistant, they're abrasion resistant, and they're also solvent resistant. And what that allows us to do is incorporate the particles at different steps, different stages of diverse manufacturing processes, and also to work them into a variety of different products. They can also be made covert. And if the video works here, you'll see in a second what that looks like. Hey, look, they're covert, right? You can't see them. What you should have seen is that when you shine a near-infrared light on them, you see the colors show up. So they can be made to where you can't see them unless you know what you're looking for. Also, you can read them out from within objects. Here, we show you a 3D printed key with our particles incorporated. When you have the illumination off, you see nothing. And when you turn the illumination on, you can actually read out our particles from within the object. And this can offer a way of enhancing the security for a variety of manufactured goods that are plastic. They can also carry sensors, believe it or not. If we just change, instead of putting an optically active element, we put a sensor into one of the lanes on our particle, you could imagine them being responsive to either temperature, pH, or specific biomolecules. So it would end up looking like this, let's say if a temperature threshold was exceeded. And we're considering that these might be very useful for the next generation of smart labels, not only authentication, but giving you some information about what sorts of conditions a product is seen. So in a nutshell, we've taken an advanced manufacturing technique developed here at MIT. We've mixed it with a very unique sort of optically active nanocrystal to form these polymer nanocomposites, which give you our very nicely colored striped barcodes, and pairing all that up with the detector you're all carrying in your pocket for decoding. And just to recap here, this is as secure as RFID for less than 1% of the unit cost. It uses your smartphone. It's tough enough to be built into manufactured goods. We've shown it in the textile industry that it can be read out from after being passed through a hot extruder. And there's also sensing capability for smart labels. And the effect we expect this to have is to enable broad adoption by both producers and consumers. And I would note that this is the only technology out there, this is our differentiator, that has both the security of central bank grade features and the convenience of easy readout. Where we are today, I'll just go through this real quick. The IP for the manufacturing process was invented in 2007. We invented the process of encoding the particles in 2011. Last year, we had our first proof of concept demo. And today, we're in the process of scaling up. And we've got several commercial pilots ongoing. Within the next year, we plan to spin out, build a team, raise some funds, and prove out the technology at a big industrial level. So if you have suitcases full of cash, please feel free to find me afterwards. Thank you very much.